Bismillahirrahmanirrahim. Today we shall start with a topic of absolute configuration in stereochemistry. The absolute configuration is denoted by R and S in case of optically active compounds or the optically active molecules. Taking one example here, which contain chiral carbon, and here this chiral carbon is attached to 4 different atoms. So basically this molecule is optically active and we have to assign absolute configuration to this molecule. So this absolute configuration would be assigned on the basis of the sequence rule of Cahn-Ingold-Prelog. According to this sequence rule, the configuration of such molecules would be assigned on the basis of the atomic number. So we will see the higher atomic number and then go down to the lower atomic number for assigning the configuration. For example, here bromine is attached to the central carbon atom and it has atomic number 35, then chlorine has 17, then fluorine has 9, and hydrogen has 1 atomic number. So according to the sequence rule, the highest number would be prior, that is bromine. It would be prior to chlorine, and chlorine would be prior to fluorine, and fluorine would be prior to hydrogen. So we can assign the priority number: bromine 1, chlorine 2, fluorine 3, and hydrogen 4. So now we shall rotate from number 1 to number 2, number 2 to number 3, and then 4. We can see here we are rotating from 1 to 2. So this rotation is anti-clockwise rotation. You can see anti-clockwise rotation. So if such situation would be there, then we say the rotation is on the left side, and this is represented by S. S means sinister, which is a German word. This is the Latin word sinister, and S has been taken from this sinister. So it's mean this optically active compound would rotate the theoretically would be considered as S configuration, and its mirror image would always be of R configuration. Here you can see the same example: carbon having the 4 different atoms. Bromine is at number 1, chlorine at number 2, fluorine at number 3, and hydrogen at 4. So we will rotate from bromine to chlorine, chlorine to fluorine, and then fluorine to hydrogen. So this rotation is clockwise rotation. You can see here, start from here and go here and then here. This is the clockwise rotation, mean the rotation is toward the right side, and it has been taken from Latin word rectus. So we call this rotation, we call this configuration on the basis of the sequence rule as R. In other way, the atom of the lowest priority as hydrogen here can be considered in rear or at the back side of the molecule as a shaft of steering wheel of a car. If we consider it as the steering wheel of a car or a bus, then the atom which is lower in atomic number can be considered at the rear or at the back side of the molecule. And in this way, it can be considered out of priority sequence. You can see here the hydrogen is represented with the dashed line showing the hydrogen that is of lowest atomic number at the back side. And then we can see the priority order in case of the other two atoms or groups. You can see here the bromine is number 1, then chlorine, then fluorine. So if we come from here to here to here, then you can see this is the anti-clockwise order. So we are going anti-clockwise. So this configuration would be assigned as S configuration. This would be the S configuration. Take one more example. This is the chiral carbon attached to 4 different groups. This is the methyl group, here CH2F group, here CH2Cl group, here CH2Br group. So this central carbon is attached directly to the carbon, also here the carbon, also here attached to the carbon, also here attached to the carbon. So this carbon is directly attached to 4 same carbon. So in order to represent the order of priority, we shall see on this carbon which atom is attached. For example, you can see here on this carbon, fluorine is attached here. On this carbon, chlorine is attached here. On this carbon, bromine is attached here. On this carbon, H are attached here. So on the carbon number 2 here, from here to here, bromine is of higher atomic number, and then chlorine is of higher atomic number, and then fluorine is of higher atomic number. CH3 is the group which has the lowest priority, and we shall consider it out of priority here. And now this group would be at the first order of precedence because it contains Br. This group CH2Cl would be the second order of priority because here we have Cl, and similarly this group has the fluorine and it would be at the third order of priority. Now if we move from 1 to 2 and 2 to 3 and 3 to 1 again, we will see the rotation. This rotation is anti-clockwise rotation. You can see here, come from Br to here, CH2Cl, and then CH2Cl to this CH2F. So this rotation is anti-clockwise rotation. So the molecule would be assigned S configuration. Similarly, if we put the mirror in between, we would get the reflection of this on this side. And you can again see this is number 1 having Br, this is number 2 having Cl, this is number 3 having F. So we will move from this CH2Br group to this group, and this to this, and this. You can see here, this is clockwise rotation, clockwise rotation. So this enantiomer, or the mirror image of this, can be represented by RS configuration. You can see here the priority order. So on the basis of the priority order, we can assign the configuration, the absolute configuration. If we can't decide on the atom which is directly attached to the chiral carbon, then we decide on the atom which would be attached to the carbon which is directly attached to the central carbon. So we'll see the priority of the atoms which would be attached on the second line. So in this case, we can see the priority order and the configuration. The S configuration and the OR configuration has been assigned on the basis of this priority order according to the sequence rule. And the sequence rule is based upon the atomic number of the atom attached to the central carbon atom at number 1 carbon or at number 2 carbon. Here we have one more example, and the priority order on the basis of the sequence rule is to be determined on the basis of the nature of the group attached. You can see this is central carbon atom attached to methyl group, and then isopropyl group, and then N-propyl group, and then ethyl group. Now the order of priority on the basis of the sequence rule would be like this. The isopropyl group would be at number 1, and the N-propyl group would be at the priority number 2, and the ethyl group at the priority number 3. This CH3 is of lowest priority, and we consider it as out of priority for the sake of the assigning of the configuration. So always the branched alkyl groups would get precedence over the unbranched in groups. So isopropyl is branched and N-propyl is straight. So here, what is the reason that the branched group would be taken prior to the normal group is that this carbon, which is attached to the central carbon atom containing 2CH3 group, directly attached to this carbon. But this carbon, which is directly attached to the central carbon, the chiral carbon, this carbon is attached only to one carbon. So this is the reason that the branched alkyl group would get the priority over the normal alkyl groups and so on. So the order of precedence would be like this. The isopropyl group would be number 1, the unpropyl would be number 2, and ethyl group would be number 3. So we can go from 1 to 2 to 3, and this rotation is clockwise rotation. So we will assign the configuration to this molecule as R. So this R is exactly the mirror image of this S you can see here. And now you can see the order of precedence. This is 1, this is 2, this is 3, and we will rotate from left to right. So we are coming left to right, and this is anti-clockwise rotation, so represented by S. Taking the example of the isotopes attached to the chiral carbon here, this is the hydrogen, fluorine, deuterium, and tritium. So deuterium and tritium are the isotopes of hydrogen. So order of precedence in case of the isotopes attached to the chiral carbon would be like this. Fluorine would be lying at priority due to the atomic number and would be number 1. Then tritium would be number 2 and deuterium would be number 3. Although tritium and deuterium having the same atomic number, but the number of the neutrons in tritium and deuterium are different from each other. So higher isotope would get the higher priority according to the sequence rule. This is because the quarks are the subatomic particles present in the neutrons would give tritium the priority over deuterium. So according to the sequence rule, on the basis of the atomic number and on the basis of the heavy isotopes, the order of precedence would be like this: fluorine at number 1, tritium at number 2, deuterium at number 3, and rotating from 1 to 2, 2 to 3, and 3 to 1 again, we shall see this rotation or this movement is anti-clockwise rotation. That is, we are going from right to left, so represented by S. The mirror image of this is this, and you can see F number 1, tritium number 2, deuterium number 3, and we rotate from 1 to 2 to 3, or we are rotating from fluorine to tritium, tritium to deuterium. And this rotation is clockwise rotation represented by R. Why isotopes interact with electromagnetic waves of plain polarized light. We can see the neutrons contain quarks with fractional charge and a small mass. The quarks can interact with electromagnetic fields because they give out electromagnetic radiation when they vibrate. So they can interact with plain polarized light. So with the interaction of the quarks in the higher isotopes, there would be the change in the angle of rotation of the coming plane polarized light to the molecule having the isotopes. So you can see here proton and neutron. Here, this is the neutron. It contains the quarks. This called as upward quark. This called down quark. This called down quark. This called up quark. So here, additionally, we can see here, we have the lines of electric field between this up quark and this down quark. This is proton, this is neutron. So proton and neutron in the nucleus, they are held together through this electromagnetic bond. This is actually the electromagnetic bond between neutron and proton. So this is due to the presence of the electric field because these are the charged particles. This up quarks, this down quarks, this down quarks, this is down quarks. So being charged particle, they have the electric fields. They also have the electromagnetic waves. So they can interact with the electromagnetic waves which would be coming externally as plain polarized light. So that is the reason why the higher isotopes would be represented as the higher atomic number. So they will behave like the higher atomic numbers. Taking the example of the ring molecules, we can see here, this is the carbon, which is the chiral carbon containing OH group and the hydrogen group. And on this side, you can see from here to here, up to here, this is one fragment which is containing the single bond and here the double bond. Similarly, come on this side, from here to here and here to here, we can see the presence of the single bond. So the side having the double bond would get priority over to the side having the single bond. So the chiral carbon attaching to oxygen, and oxygen is the of higher atomic number. And on the other side, the chiral carbon is here and here attached to the carbon having single bond and carbon having double bond. So this side would get priority over this side. In this way, this would be the number one, and this fragment, or you can see the group, would be of number 2 priority, and on this side, this group would be of number 3 priority. So we can rotate from 1 to 2 and 2 to 3 here. So this rotation would be anti-clockwise rotation. So here, this molecule would having the S configuration. So the carbon would be configured as S. The mirror image of this molecule is this, and you can see the OH number 1, then this side is number 2, and then this side is number 3. So we will rotate from 1 to 2, 2 to 3. And this rotation is clockwise rotation, you can see. So the configuration of the chiral carbon, all this whole molecule would be R configuration. Here is an exercise for considering your understanding about the RS configuration. So this is question number 1. Here in this molecule, you have to see the symmetry element, because we have taken the lecture of the optical activity and we have discussed about the symmetry of the molecules. So you have to search about the element of the symmetry here in this question number 1. And question number 2, you have to seek about the chiral carbons. Where are the chiral carbons? And you have to assign the configuration to these chiral carbons. First of all, you have to search the chiral carbons, then assign configuration to the chiral carbons. Exactly like RS configuration, which is based upon the sequence rule of Cahn-Ingold-Prelog, we can assign the absolute configuration to the geometrical isomers. And these configuration are represented by E and Z configuration. Taking the example here, this is basically geometrical isomer. You can see this is the carbon number 1. This is the carbon number 2 of the alkene. So on this carbon, we have hydrogen and bromine. So on this carbon number 1, bromine has more atomic number as compared to the hydrogen. And on this carbon number 2, chlorine has more atomic number as compared to the hydrogen, you can see. So you can see at carbon number 1 and carbon number 2, we have chlorine and bromine. The purity of chlorine is more at carbon number 2, and it is on this side. At carbon number 1, the bromine is prior to hydrogen. Now bromine and chlorine both are on the same side of this alkenic bond. So because the atoms which got the priorities on the carbon number 1 and carbon number 2 are on the same side. So this configuration would be represented by Z. And this comes from zusammen. This is the German word, zusammen, mean together, mean on the same side. So the configuration is Z configuration. You can see this is also on the basis of the sequence rule. Taking the example again, this is alkenic carbon number 1 and 2, having the carbon having the double bonds. On the carbon number 1, Br is having the priority over hydrogen, and at carbon number 2, Cl is having the priority over hydrogen on the basis of the atomic number. Now you can see the chlorine and bromine, they are higher in atomic number on their own carbon atoms. That is carbon number 1 and carbon number 2. But now they are on the opposite side to each other. This is on this side, this is on this side. So they are on opposite side to each other. In this way, we called this configuration as E configuration. E is taken from the German word entgegen, which means on opposite side. Similarly, see here, Cl and Br, they are on the same side. So this is Zusammen, represented by Z. Here you can see Br is prior to hydrogen, Cl having more atomic number than fluorine, but on this carbon, Cl is opposite to the Br on this carbon. So this configuration is assigned as E. Taking more example, here this is the alkenic bond, this is the carbon, on this carbon, this is the ethyl group, this is the methyl group. This ethyl has the priority over this methyl group, and on this carbon, this CHO bond, that is the aldehydic bond, has the priority over CH2OH bond. Why the CHO bond would be prior to this? This CHO bond would contain this CHO bond would contain C double bond O, and this C double bond O would be considered as oxygen is attached to this carbon for 2 times. So that is why this CHO group would take the priority over this group. So the priority groups are on the same side. So Z configuration, the priority groups on the opposite side, E configuration. Similarly, come to here. On this carbon, ethyl is prior to methyl. On this carbon, chlorine is prior to ethyl. So chlorine and ethyl are on the opposite side. So in E configuration, and in here, they are on the same side. So this is the Z configuration. So this was some about the easy configuration to give the understanding in case of the RS configuration, always, as well as in case of the AZ configuration, and all the configuration assignments are the assignment of the configuration is working upon the sequence rule, which mainly depends upon the atomic number, the basis of the direct atoms attached to the chiral carbon, or the chiral carbon attached at second or third line, or on the basis of the isotopes, or on the basis of the nature of the alkyl groups. Thank you.